EZ isomerism is the first type of a stereoisomerism that we're going to see in the AS course. If you think of your alkanes, an alkane has lots of sigma bonds joining the carbon and hydrogen atoms together. All of those sigma bonds can rotate. We can rotate this molecule in 3D space. And so if we were to draw this and this, they would actually be the same molecule. They would not be isomers at all because they are in the same molecule. They've got the same structural formula, they've got the same molecular formula, they've got the same arrangement in space, or at least they can do if we rotate them around a bond. Look, that one there, and then this one here. We can make that molecule into that one just by rotating a bond. Now we're studying alkenes. We have such a thing as a pi bond, and here on this model my pi bond is represented by the above and below the plane of the molecule bonds like that. Okay, now there's a sigma bond in the middle which is still rotatable, but the pi bond itself would have to actually be broken in order to rotate. The bit above and below the molecule are fixed. Unless I actually physically break that bond, I can't turn it round. And that gives us with a possibility of a molecule which looks like this, and a molecule which can look like this. Now I could change the alkane between these two forms, but what I can't do is I can't rotate the pi bond, so this cannot change into that, and this gives us molecules with slightly different properties. The boiling point of these will be slightly different because each molecule has a slightly different surface area of contact, and that leads to different London forces and therefore a different boiling point. It's very, very subtle, it's very, very small, but actually it is there and it is important. So we call these stereoisomers, and stereoisomers are molecules which have the same structural formulae but different arrangements in space. So we can see that the arrangement in space here and here is different, but the structural formula, if I was to write it here, would be CH3, CH, CH, CH3, and the structural formula of this one would be CH3, CH, CH, CH3. So there's no difference in these two formulae, but there is a differene in the arrangement in space. So we need a way to separate these out when we're naming them. So both of these are but2-ene, and the only difference is that we have them with the two methyl groups here and the two hydrogens here together, and here we have them on opposite sides of the molecule, if you like. So we'll describe that as each carbon atom making up the carbon-carbon double bond has two different functional groups on it, and then we can get this different isomerism. If the two methyl groups are opposite each other, they are across the molecule, we have two ways that we can describe that. We can say that they are E, which stands for the German entgegen, which is opposite, or we can call them trans, which is the Latin for across, transalpine, transatlantic. The other one, because we have them together, again we can turn to our German and we can go Z for zusammen, which is together, or you may like to remember zugether. We can also call this by the Latin, which is cis. So when do we use each one? Well, if we are talking about Cis Trans Isomers, then we must make sure that we have a hydrogen as one of the groups on each carbon atom that's making up the double carbon-carbon bond. Because these two are hydrogen, we can call this cis because the two hydrogens are together. Because these two are hydrogen, we can call this trans because the two hydrogens are opposite each other. Okay? If we have different functional groups on there, no hydrogens or only a hydrogen on one of the carbons, we can't use cis-trans. Okay, that's reserved specially for when we have a hydrogen on each carbon that makes up the double carbon bond. So some things you can call cis, and that's perfectly fine. to call them cis, and it's perfectly fine also to call them Z. Some things you can call trans, and it's perfectly okay to call them E. It works for some molecules that you can name them using either system. Okay. However, if we had something which looked like this, we would find that we don't have two hydrogen atoms on either carbon in the carbon-carbon double bond. So we have to have a way of working out which way is E and which way is Z. Now for this one we could have a couple of ways of doing this. We could say, right, well, we've got methyl groups on opposite sides, so let's call it E. Or we can say, well, this is a heavier group and this is a larger group, this is a smaller group, this is a small group, so we could call it Z. And that's a little confusing. So we have a system of rules which helps us work out which system there to use. So we call this system the Cahn-Ingold-Prelog after the three people who thought it up. And the way that we do it is we look at a molecule and we assign high priority and low priority to the groups on each carbon. And we do that by the atomic number. So if we have a higher atomic number, we say that that is a higher priority. Okay, so if we look at the first carbon atom, we have over here, we have a bond to a carbon and we have a bond to the hydrogen. Hydrogen has an atomic number of 1, carbon has an atomic number of 6, therefore we have the high priority with the CH3 as it's got a higher atomic number, and we have the low priority where the hydrogen is, because it's only got an atomic number of 1. On the other side, we're looking for a higher atomic number, but actually carbon and carbon are both 6. So what we have to do now is we have to go, right, okay, well, if that is 6 and that is 6, what's the next atom along in the chain? We're going to look for the first point of difference. So here we have a carbon which is 6, here we have a carbon which is 6. If we go along one bond in this group, we're going to find a hydrogen because that's all that's left. Here though, if we go that way there's a hydrogen, no different. That way there's a hydrogen, no different. Here though we go to the next atom which is carbon, which has an atomic number of 6. So therefore we assign this the high priority because it's got the higher atomic number at the first point of difference, and we assign this one the lower priority because it's got the lower atomic number at the first point of difference. And therefore, because the high priority groups are on opposite sides, we would call this one E. So if we have a look at this molecule, we've got a larger group there which is a little bit of a red herring, and we've got 3 other atoms around this double bond. So we're going to look at this carbon atom, we're going to say, right, fluorine and chlorine. Fluorine has an atomic number of 9, chlorine has an atomic number of 17. Therefore we have a high priority with the chlorine, the low priority with the fluorine. If we have a look at the other carbon atom, bromine has an atomic number of 35, whereas sulfur only has an atomic number of 16. Despite the fact that there are more atoms here, we're going to go with the high priority being the one with the higher atomic number at the first point of difference. So we're only studying the first atom where it's different. So this one would also be E. So having a look at this one, 35 for bromine, 53 for iodine. We're going to go with the high priority one with the largest atomic number, low priority there. Here we're going to have to look for the first point of difference, and we start with the carbon. Then the next atoms are 2 hydrogens here, and here we have 1 hydrogen, 1 carbon. So the carbon has an atomic number of 6, the hydrogen here has an atomic number of 1. Therefore, this is the low priority, this is the high priority, and we call this one Z.